Today we're going to finish talking about Chapter 12 on gradient boosting. And what we're going to cover today is a particularly powerful implementation of gradient boosting in R. And then we'll use this also to look at the general idea of how you do feature interpretation for gradient boosting machines. So what we're going to talk about for most of today is what's called XGBoost. And you'll do a little bit with this on homework assignment 3. So what this is a package that's available in R and elsewhere called, what it stands for is extreme gradient boosting. And the name is a little bit dramatic, but it's not really anything more than taking gradient boosting and adding lots of additional options and features to it that we can implement. Okay, so this builds on standard GBM packages. By adding many additional options. Perhaps the most interesting ones, and the ones that we'll spend the most time talking about, are regularization type options that allow us to attack the bias variance trade-off if we observe overfitting. So we talked about regularization in the context of regression in Chapter 6. So now we're going to see it come up again, and we'll also see it come up in Chapter 13. Okay, so that's going to be our first additional option, so regularization. Okay. So XGBoost can deploy several different, and we'll see even ones that are different than what we've seen before, regularization parameters. And so just as a recall of what regularization is, you can see Chapter 6 for discussion in the regression case. That can help with overfitting. And we'll see this specifically, how they affect the difference between the train and test errors. All right, the second is early stopping. And here we don't actually mean necessarily early stopping with regards to, we don't mean early stopping with regards to growing individual decision trees, but with regards to training the algorithm itself. Okay. So what we mean by early stopping is that model assessment stops. Okay. So which is improving runtime. So the idea is we stop computing, so it takes less time for the model to run. If satisfactory performance thresholds are obtained. What is that? What that roughly means is that if we're running the model and the loss function, we set some threshold essentially saying that perhaps once the loss function value is below a certain level, then we will say the model is good enough and we'll stop training. Okay. So that's one way to think about it. Or if error reduction does not exceed some percent threshold. So what we mean by that is suppose if you're training the model, so there's two ways then of implementing early stopping in XGBoost. One is to simply set this threshold at which point, if the loss function gets below that, you stop training. The other is to say, okay, if additional model runs aren't improving the error by a large enough percent, in other words, if we're seeing the error stabilize, then you can tell the algorithm to stop. Okay. So this will prevent more iterations. So in other words, we'll stop growing more trees if we don't see a big enough improvement in the error. Okay. So both approaches will decrease runtime. Okay. A third option that XGBoost can implement, which is also for runtime, is parallel processing. Now, there's a lot of limitations here. Unlike with random forests, we can't grow the trees in parallel because, of course, the trees are dependent. Okay. What it can do is it can distribute around some of the computational tasks. Okay, so XGBoost can implement some distributed computing distributed processing engines to provide computational parallelization. So it's not parallelization at the level of random forests or bagging algorithms, because you can't grow the trees in parallel, since you need to have grown a tree to grow the next one. But you can do some of the computation in parallel. So this also improves runtime. Choice of loss functions. So these can be totally customized. In XGBoost. So what I mean by this is, in other packages like GBM, there's lots of loss functions already built in. But in XGBoost, if you wanted, you could essentially build your own loss function. So you could make it from scratch if you had some particular formula you wanted to use as a loss function, rather than just kind of working through one of the standard ones. Okay. Like GBM and some of the others, base learners are customizable. So in XGBoost, decision trees can be replaced by any base learner. Has a nice option called continue with existing model. And what this means is that training results and partial model runs can be saved and return to without starting over. So you may, in particular, if you're doing a long, say, model training run or long grid search and so on, you may, for whatever reason, need to you might need to stop somewhere in between, for whatever reason. Maybe you have something else to do, or you need the computing resources for some other task, and so on and so forth. So you can essentially just save your in the middle of your process in XGBoost and then restart later. So that's a nice little option available. And then XGBoost is available across lots of languages and implementations. So XGBoost can be implemented in, just as some examples, R, unsurprisingly, Python, Java, C++, and some other languages as well. And in R specifically, there are several ways it can be implemented. There's a package specifically for it called XGBoost, and this is what you'll use on assignment 3. The assignment goes over how to implement it. It can also be done in Caret in H2O, so some of these meta engines can implement the XGBoost protocols and others as well. So it's kind of very flexible, and so in particular, if you're working in it, you can port it over, say, from R to another language if you have to, or if you're sharing it, say, if you're working with a team, it provides kind of a nice flexible environment to work in if you want. Okay, so a lot of those features have to do with sort of real life implementation, when you're actually so the meta implementation thing, the return to model, etc., and run are kind of about runtime. But I want to just go back to the start. The first one, in some sense, is the most important from the perspective of adding additional performance features, model performance features to gradient boosting. So now we're going to include regularization, and so there's several ways to do this. And so this adds some additional hyperparameters. So this is what we'll spend most of today talking about. So the other aspects of it are just some nice examples of extra features available. But regularization gives us some new hyperparameters, which then we need to incorporate into our tuning strategy from last time. Okay, so the first are what we would call standard regularization hyperparameters. In some sense, what these are going to be, these are hyperparameters or regularization hyperparameters that mimic essentially the ones we saw in chapter 6. So they're just analogs of all of the regression ones. They just have different names here. Okay. So the first one is what's called gamma. Okay. And then we'll see ones which are, so alpha and lambda, I don't know why these are the particular names that got picked, are going to be ones that essentially do L1 and L2 regularization like we saw in chapter 6. Okay. So what gamma does essentially is it controls in some way tree complexity. Okay. So it's a tree growing sort of hyperparameter, additional one. But how does it do this? What does it specifically do? So gamma, what it does to control tree complexity is gamma specifies a minimum reduction in loss function required to make a split at a node. Okay, so in other words, what it's going to do is it's going to stop the tree from growing if making an additional split doesn't give a large enough reduction in the overall loss function. Okay, and it does this in kind of a roundabout way. So gamma implements this by fully growing a tree to max depth. Okay. But then pruning it back so it does this kind of in reverse. Okay, so it grows the tree fully out, but then it pruning it back by removing any splits that do not meet the threshold. So the idea is it works backwards. So it starts from the leaf nodes, and then if any leaf node split, if that split didn't produce a large enough reduction in loss function, it deletes that split. And so then the ones at the previous step become leaf nodes. And it iteratively works backwards in that way. Okay. The values of gamma range from 0, which is just no constraint, to, well, I mean, to infinity. So there's no kind of upper bound, or there's no normalization here on kind of the values it can take. And this is because there's no way to say what large or small means here. Like usually we have at least some general heuristic of what is a large or small value, but it depends on the loss function. Large versus small depends on the specific loss function. Because different loss functions, of course, produce very different types of values. So there's no way to say here for sure. So you have to kind of have some idea of balancing this out. Okay. So implementing gamma can be very useful if we observe large differences or large discrepancies in the training and testing errors. Because a large difference between the training errors, in other words, like the model, the validation as we go, and the testing error, that's a good indication of overfitting. Okay. And we'll see this in a little bit. We'll bring up an image to kind of, it'll just sort of generally describe regularization without kind of talking about these very specific parameters. But we'll see this is actually what happens. Okay, so this is one way of introducing regularization to try and prevent overfitting. Another way is with what are called alpha and lambda, two additional hyperparameters that are similar to what we've seen before. Okay. So lambda gives L2 regularization, where you're looking at sort of the sum of squares, and alpha gives L1 regularization, where you're looking at absolute values, sum of absolute values. So if you just I'm not going to like formally define these, but L2 and L1 regularization are what we saw back in chapter 6. So if you just want a refresher on that, go take a look at it. Now the formulas, it's a little bit different because now we don't have explicit coefficients like in regression, right? But it's the same kind of idea. So like with gamma, the range of values is 0, so no regularization, to infinity. And just like with gamma, what's big depends on what kind of loss function we're working with. But basically, we'll just simply make the following observations, without talking about large or small. So if lambda is positive, so we're introducing L2 regularization, this is similar in behavior to ridge regularization that we saw for regression. Okay, what does that mean by similar to ridge? It means if introducing this lambda parameter reduces the effect of noisy, irrelevant, and collinear features. So those kinds of problems get handled by positive value for lambda. Alpha greater than 0, similar to lasso. In that it provides some automated feature selection. So it will completely kill off some features, potentially. Okay. And then both greater than 0 is similar to ENETs, where you implement both aspects, but then takes corresponding, you increase your training time because you're tuning two hyperparameters. So implements both aspects. But tuning two hyperparameters increases runtime. So there's a trade-off there. And just like I said with gamma, like what we mean by smaller and higher values depends on the loss function, but generally speaking, higher values, depending on, of course, the loss function. What will that do in general? Generally, will limit the influence of individual leaves. So that's kind of what you'll get out of that. All right. There is another approach to regularization, which we give a different name to, but it's another regularization type approach to minimizing overfitting. And this is one that we'll see in more detail in our next chapter, and it's what's called dropout. Okay. So an alternative approach so regularization type approach to reducing overfitting and which is especially popular for what we call deep neural networks. And so this is just a little preview of chapter 13. But it can, as we'll see here, this approach of dropout can be implemented in XGBoost for gradient boosting. Okay. And so what dropout is based on here is an observation. Okay. So in gradient boosting machines, the earlier trees grown. So in other words, the first iterations in the model run tend to be most influential on the overall model. Okay. Why? Well, because we grow the initial trees are going to start the process of training, sequential training with respect to errors. So the errors of the first tree are what the second one gets grown on. It prioritizes is patching up those, and so on and so forth. And so the initial trees in the sequence are going to kind of lead the process in some sense. Like it's going to you're going to go down this this path of training on the errors coming from those ones from the first few, and then it's just going to kind of keep going down this direction. Okay. And so the idea then is if we want to avoid that, what we can try to do is avoid training on some of the trees. Okay. So the idea is to randomly drop trees in the boosting sequence to prevent overfitting to the specifics of the sequence. Okay, so in other words, what we're doing with dropout is we're introducing randomness to reduce overfitting. And improve generalization performance. So this is one of those, this is an idea, a general idea that we've seen many times in the past, that introducing additional randomness can help to break up structure that causes overfitting, where the algorithm kind of just zeroes in on the structure of the data and of what's already been looked at and in the algorithm training process. And so by throwing that extra randomness in, you'll avoid this. Okay. So for gradient boosting machines, this is often called DART. Machine learning people really love their acronyms, right? That stand for something, that have some kind of name. So DART here stands for Dropout Additive Regression Trees. But it can be implemented outside of regression, although that's the place where it was first done. And typically, of course, we do a lot of regression algorithms. But that's, so I think the name they came up with was something that would create a nice, they call it, sometimes you use the term backronym. You figure out what the acronym you want it to be, and then you fit the words into it. All right, so how do you implement this? There's a hyperparameter for it. The associated hyperparameter is the proportion of trees to drop out of the boosting sequence at each step. So proportion between 0 and 1. 0 is simply not including this dropout regularization approach. Obviously, you're not going to use 1 because that would drop everything out. So somewhere between 0 and 1, if you want to implement this, is what you would use. Okay, so let's talk about now what the tuning strategy is, and then for including these regularization parameters, and then see what the effect is on perhaps on the model, okay, on the model performance. Okay, so it's the same idea. We're not going to go through it in as much detail because we can summarize what we've already done. So the same idea as for what we call basic gradient boosting machines and for stochastic. So remember, we have this tuning strategy for the basic process, and then we showed where you can introduce the stochastic parameters in addition. And then what we'll do is we'll see now where we can implement these regularization parameters on top of that. Okay, so increase number of trees and tune learning rate or shrinkage, whichever term you like to use here, with early stopping. So early stopping, remember, an XGBoost is referring to, we'll stop the process if we reach a certain error threshold, or if we're not getting enough improvement. So that's a good way to sort of tune or do a grid search, right? Because then you won't run your grid search longer than necessary. Then tune tree-specific parameters, so depth and minimum node size. So look for any improvement from introducing stochastic hyperparameters. So as we discussed at the end of the last class, these can be introduced at the end of the tuning of the basic model, or they can be introduced kind of at partway through. So then we think about regularization by looking for overfitting. So if overfitting is observed, so that's going to be large train versus test error differences. Look at implementing regularization and or dropout. Okay. Then, if things have changed a lot from the start, retune the learning rate. so the shrinkage, if our new hyperparameter values differ significantly from the defaults or from the earlier ones. Okay, and then obtain a final model. Okay, so I'm not going to go through the additional details of this with the Ames example. I'll let you take a look if you want. So see the Ames example in the text. For details. A lot of it is similar to what we did before. Some of the grid searches take a lot of time, but let's take a look at. So let's see the result, including regularization. So we're going to look at an image here. I think hopefully we'll do a nice job of illustrating this. Okay, I need to share. So what's going on in this image is the following. The two solid lines are the training and testing errors when there is no regularization. Hopefully you can see the colors are coming through. So the solid kind of blue teal line, that's the training error for so the training error without regularization, and then we're just measuring in some sort of normalized form of root mean square error, okay, just so that it's easier to compare. And then the solid kind of pink red line, that's the testing error without regularization. So notice how big the gap is between those, right? The training error gets fairly close to zero. It's very small after a lot of iterations, but the testing error levels off very quickly at a much higher number and doesn't really decrease. Okay, that is a good indication. That big gap between those and how quickly they both sort of leveled off, a big difference between them. That's a good indication of overfitting. The model is overtraining to the training data. It's overfit to the training data, and then when we try it on out of sample data on the testing data, we get a much bigger error. Okay. So visually, this is kind of what overfitting will look like when you have it in your model. So now the dotted lines are when we introduce regularization. The dotted teal line is the training error, and the dotted red line is the testing error. Now notice that the gap between them is much smaller. Also, it appears that they're still both of them are still sort of starting to decrease at the edge of this, so we might want to go further. But this is good. So you might say, well, the testing error is bigger than for the without the regularization, but that's not really, it's not the absolute error necessarily that we're concerned with, but rather the gap between them here. If we're looking for overfitting, a big train versus test gap indicates that. Here we see now with the regularization a much smaller one. So this is an example where really introducing regularization has a very positive effect. Okay, so that's the kind of thing visually to look for when you're talking about overfitting. It's a nice. This is a nice illustration of what overfitting kind of looks like when it's plotted. All right, so then the last topic that we'll discuss for gradient boosting is feature interpretation. And here we'll take advantage of XGBoost as well. But this applies more generally, not just for this specific package, but just in general to gradient boosting. Okay. So GBMs have a similar limitation to random forests. Okay. Namely that aggregation makes it difficult to directly interpret feature importance and effect. So it's just hard to say what specific effect a particular, say, feature is having on the model. So what do we do? Just the same thing as with random forests. So as before, we focus on the overall reduction in loss function and related measures, other kind of aspects related to this. Given by the features. Okay. So in XGBoost, there are now 3 ways to look at this. We'll introduce the names and then we'll kind of work through an example here in a moment, like kind of a sort of an easy sort of example, kind of contrived example, but one that allows us to actually calculate by hand. Okay. So the first is what's called gain, and this is equivalent to impurity measure that we've already seen. So for random forests. So simply, and then in some sense, measuring kind of total reduction in loss function. Then there's one called coverage. What this does is it measures the relative number of observations influenced by each feature. So the name comes from the idea that it's sort of measuring in some kind of relative way, some percentage way, like what percent, some sense of the data does each feature have, like is that feature important for? And then we have one called frequency. This measures, it's another relative measure, the relative number of times a feature occurs in the splits, so in the various tree splits. So in other words, so frequency is in the sense of the frequency of a particular feature being the splitting feature, right? So this is actually, in some sense, it's a kind of a natural way to think about a feature being important. If you're splitting on it, that's suggesting that it's influential for the model, right? That it's that it is important for the structure of the data. Yeah, so it's actually kind of makes a natural sense to look at it. Okay, so here's an example. I want to just go through an example to explain how coverage and frequency work. Okay. So I said this example is going to be kind of contrived because it's sort of, we're going to use very small numbers. So we're going to have 100, we're going to say we have a data set that has 100 observations, obviously not very many, and has only 4 features. So again, not very many. And then we're only going to have 3 trees. Now, obviously, in any real model growing situation, we're going to have a lot more than that. But so that's why I say this is kind of contrived. The numbers are all small, but just to make things easy. So I'll call the trees T1, T2, and T3. All right. So let's say that the features are X1, X2, X3, and X4. And so X1, let's say, is used to determine a leaf node for 10 observations in tree 1, 5 observations in tree 2, and 2 observations in tree 3. Okay, so then what coverage does is it just counts all these up. So coverage counts 17 for X1. So basically what it does is it adds up the number of times it determines a leaf node. Okay. It repeats for X2, X3, and X4. And it expresses the results as relative proportions. So what we mean is we take the number that we've counted for each, so the number for xj, divided by the sum of the numbers for all of them. So say a sum from k equals 1 to 4 of the number for xk, okay, for each j, for j equals 1, 2, and 3, and 4. So that gives you your coverage proportion for feature 1, feature 2, feature 3, and feature 4. Okay, what about how would frequency work? So let's also say that X1 is used for, and let's say it's 2 splits in tree 1, 1 split in tree 2, and 3 splits in tree 3. So we split on that feature that many times. Okay. So then we add those up, and we'll say that this gives X1, we'll call it weight 6. So we just add up the number of times it occurs in the splits. Okay. And then we repeat for X2, X3, and X4. So we determine those sort of these split weights. And then the frequency for j equals 1, 2, 3, and 4. So for each of the features is the weight of feature xj divided by the sum of all the weights. And so that gives you then a proportion. It's a relative measure. So okay, so these are that's just kind of trying to explain then how these things are measured. Let's actually look at an example. Not too surprising. Let's look at the Ames example. But what happens when we do gradient boosting, feature importance? How does it compare with RF? So GBM versus RF feature importance. By looking at gain or equivalently impurity. Okay. So let me pull up the images first. Okay, so here's, and the display is a little bit different, but here's what it looks like. Here's like the gain measure of importance for in XGBoost for the Ames housing data. So this is gradient boosting. Okay, so what do we see? Overall quality is by far the most important. Greater living area, second. Garage, how many cars fit in the garage? Year built. Okay, so some various features of the data. Some of these we've seen before. Okay, so let's keep in mind just a few of these, kind of read over them. Okay, let's jump real quickly to the RF one, which we've seen before. We'll bring it back up. There were two ways of looking at this, impurity and permutation. So just take a look at the impurity one. Okay, overall quality is, again, by far the most important. Then we have neighborhood, exterior quality, greater living area, first floor square feet, garage cars. Okay, and I won't pull the other one back up, but overall quality, greater living area, garage cars, year built, basement square feet, first floor square feet. Those are all among the important ones, and those are all showing up here too. Basement square feet, first floor square feet, garage cars, exterior quality, overall quality is number one for both of them. What's the big difference between the two? I mean, it's more obvious you've got both of them in front of you. Notice that in the RF importance, both here the impurity measure and if you look over at the permutation one, same thing. Neighborhood is one of the most important characteristics, right? It's one of the most important features. It's second in the impurity measure, but then going back to the XGBoost gain measure, neighborhood doesn't show up at all. It's not even that it's not second, it's not even in the top 10 now. All right, so let's make that observation. Go back to the talent. So they are relatively similar. With one notable exception. What's that notable exception? The neighborhood feature has dropped off entirely from the top 10 in GBM, whereas it was number 2 or 3, depending on which measurement we're looking at in RF. So the obvious question would be why? Okay. And this comes back to just one fact about XGBoost that I'll mention here. So XGBoost, the package used here, requires data prep of various types. The features have to be assembled in a matrix. The response values have to be in a vector. In particular, categorical features must be numerically encoded. And why does neighborhood drop away? It just has to do with how it's encoded. So this encoding can affect these measures of feature importance. Whereas if you go back and look at the images, all the variables that are already numerical are not going to be the types of variables that are going to be affected by this, right? And so they maintain their relative kind of positioning, overall quality, greater living area, first floor square feet, number of cars that fit in the garage. So these kind of numerical variables didn't move around very much. Okay, so this is just something to keep in mind. When you do encode categorical variables numerically, that can affect, of course, how they're being interpreted by the loss function. Whereas, with categorical variables, their effect on the loss function, it just depends. I mean, yeah, in the case of RF, we don't need to encode them. They can be used as is on the splits. And then we're splitting the target variables, the target values, which are numerical in this case, right? So the target value, remember, for the Ames example, just like for the project is selling price of a real estate property, a house. And so say when we're splitting on neighborhood in a decision tree, we're kind of trying to partition by neighborhood at a split into and as much as possible on the selling prices to minimize the root mean square error. Okay. But when we numerically encode things, it can kind of mess that up a bit. So it's hard to actually see this. You can't really write it down, but in an easy way. But that's the problem. So you just have to keep that in mind. That numerical encoding of variables in a package like XGBoost can have some effect on how the model interprets them. Okay, so that's it for gradient boosting. And as mentioned, next week we will shift gears quite a bit in some sense, and we're going to move out of talking about tree-based models, and we're going to talk about a very, very interesting topic: neural networks. No pun intended, although I'm going to say it a few times. Deep neural networks are a very deep subject. There's a lot you could say. We're only going to scratch the surface, and even there, we're going to still have quite a bit to say. So we'll do a few weeks talking about those ideas. In the meantime, assignment 3 is formally assigned tomorrow. If you're having any issues with assignment 2, or you need any extra time to get it submitted, just let me know. And then next week is the project outline, and I have a few questions about that. It doesn't have to be very long. It's mostly about what I want to really see is that you've looked at the project description, that you downloaded the data and opened it. Really just that you've kind of started to think a bit about the project, that you thought about, okay, well, what's the target variable? What are some techniques that we could use to model? What are some good modeling methods that might apply here of the ones we've learned? And that's basically kind of going to be it. I want you essentially to restate the problem in your own words, not just copy paste what I've written down as the project problem description, but just kind of restate it and explain kind of how, in a non-technical way, what it means. And so it should not be very long. Half page to a page at most is what I'd probably expect the outline to be. So that's not due until next week, but I just figured I would mention that. So that's it for this week, and other than assignment 3 tomorrow. But if you have any questions about anything, please just get in touch with me.